Good morning, everybody. I hope you can hear me okay. So we're going to talk about some more physics today. Before I get started on the physics, I think I'm going to hold off on talking about our first test until we get the long problems marked, and then we can talk about what it looks like. I did make some announcements over the weekend on Friday and yesterday, I think it was, in Canvas. So make sure you keep up on the announcements in Canvas, okay, because that's where I tend to say things to the whole class. Yes, can you guys hear me okay? Hopefully you can hear me. Yeah? Okay, good. Thank you. Also, just to point out that I posted the second written homework assignment. So the problem is in Canvas. There's two answers, two numerical numbers to put in, and then you submit the work in CrowdMark by Friday at almost midnight. Okay, and I will have office hours today, so if you have questions about things, you can ask during office hours. I believe that Rasul, unfortunately, is still sick, so he's not here to help us with questions again, so I'll do my best to try and answer questions as I go along, okay? I might miss some, so bear with me on that. All right, so I think that was most of what I wanted to say for now. Are there any quick questions about any of that? I don't know what's wrong with the final question. What is wrong with the final question on the bridge assignment? I haven't had a chance to look at the piazza yet. If there's something wrong with it, I'll just make it worth nothing. But I don't know what the problem was. Oh, it refuses. Oh, goodness. All right, let me check on it. Okay, and I'll make sure it doesn't hurt your marks. Okay. Oh, that one where it says rate the difficulty? That one. All right. You know what? I'll try and figure out what's wrong with that. That was a new one that someone gave me to use, and it sounds like it's not working. All right. So don't worry about that. All right. So let's try and do a little bit of physics now. So we are on to chapter 5, which is also about forces. We're going to do some more specific applications of forces. We're going to be looking at centripetal force, which is the force that basically causes things to move in uniform circular motion. And we're going to be looking at friction. So let's see if I can get this to work. Okay. So as you saw, this is one of my favorite cartoons about centripetal force. It's basically sort of playing on this idea that sometimes people get confused between centripetal force and what's called centrifugal force. And basically what James Bond says in the second frame, that there's no such thing as centrifugal force, is probably the right thing to think for us, because centrifugal force is what they call a fictitious force. It's not a real force. It's a force that appears to be acting in certain scenarios. So we're not going to worry about that force. We're not going to use it in this course. What we are going to use is centripetal force. But before we get to that, we are going to look at friction. So we saw this picture before. The idea that what is friction? Well, friction is the force that resists sliding motion. It resists the motion when two objects are sliding across each other. You know, you can use friction to warm up your hands, right? We'll talk more about that when we talk about energy, how you can turn that rubbing into heat. And the idea is that friction always points opposite the direction of the motion or the attempted motion. So things aren't always moving when you get friction. In fact, the first kind of friction we're going to talk about is when one object is at rest relative to the surface, okay? Or if it's two objects that are at rest relative to each other. And when that's the case, then we call the force static friction, okay? And it's the force that resists the attempted motion. So something is causing those two objects or the object on the surface to want to move, and static friction is stopping it from sliding. And we're going to use little f sub s for our static friction. And one of the most important things to realize about static friction is that it doesn't have one fixed value. It does have a maximum value, which we're going to write as F sub x, max. And the maximum value, okay, of static friction is always equal to mu sub s, which is called the coefficient of static friction, times the normal force, the magnitude of the normal force. Okay, so we know our normal force, that's the force perpendicular, right, to the surface. So here's the normal force on the block due to the floor there. Okay, and that coefficient of static friction is a number, usually less than 1, but not always. But in most cases, it's less than 1. It has no units, so it's just a number. Okay, it's always a positive number. All right, because we're talking about the magnitude of a force. So we know F sub s max, which is the maximum magnitude of the static friction. That would be a positive quantity. And n is, of course, the magnitude of the normal force. And the inequality just tells you that when in every single scenario, the static friction acting is always less than or equal to this maximum value. Okay, so static friction varies in size up to a maximum value. And you get the maximum value just before the object starts to move. So if you're pushing on it or pulling on it, okay, or one object is riding on top of another object and it's just before the top object slips, that's when your static friction will be its maximum value. Okay, the other kind of friction we'll see is what's called kinetic friction, and that's the friction you get when an object is sliding relative to the surface you're looking at. And we'll use little f sub k for kinetic friction. Okay, and the magnitude of the kinetic friction is always equal to the coefficient of kinetic friction, mu k, times the magnitude of the normal force. And again, mu k is another one of these small numbers, positive, and typically less than the static friction coefficient. In rare cases that they are equal to each other, but in most cases it's less than the static friction coefficient. Okay, so I thought we'd have a quick look, go back to our forces and motion PHET for a second here. Okay, so I'm going to stop sharing this. And we're going to find our PHET. There it is. Okay, hopefully you can see this. So this is the forces and motion basics PHET, and now we're looking at the one called friction. Okay, and the way this one works is you can see you can adjust your friction over here. Okay, and you can show the forces themselves. So if I basically apply a force here, okay, so actually my little wooden man is applying a force on the block. And notice you can see the applied force that the man is applying by pushing on the block. You can see the friction force that's resisting the motion here. And now the block's not moving, so we know what kind of friction is that if the block's not moving. Anybody want to tell me? Static, yeah, so this is static friction. And we can see then that the sum of forces is 0. Okay, those two forces have the same magnitude in opposite directions. And if we plug in the values, we can see, yes, they're exactly the same size. Okay, so in this case, the static friction is equal to 50 newtons, equal to the size of the applied force. And that's what's going to happen if an object's not moving, is your static friction will equal the net force in the other direction. Okay, and now I can crank up the force to 100 newtons. Okay, so now my applied force is 100 newtons. And my friction force has to increase to match it. Okay, so here's the friction force value varying. And now it's up to 100 newtons, and yet my object's not moving because that's not enough force to overcome the maximum static friction. Okay, so now you can keep going. Say we apply 150 newtons. Now that's enough force to overcome the static friction. In fact, I'm going to pause it there for a second. Okay, and now you can see that there's a net sum of 56 newtons in the positive x direction, and that's because we're applying 150 newtons. That's what the guy is pushing with, but we've started to move. So now we've switched to kinetic friction, And the kinetic friction, which has a fixed value, that mu k times normal, is equal to 94 newtons. And so now the block will accelerate in the positive x direction. And now you can play around with this. You can reset it. You can reduce your friction if you want to. It's kind of fun to play around with it and see what happens. Okay, so here now, with less friction, 50 newtons is enough to get it going. Okay, so now again, now we have a very small net force of about 15 newtons. Let's try one more time. Say I go about there. Now I think 50 is not quite enough to get it going. Okay, but I can slowly increase the applied force. See how they go up together, the applied force and the friction force. And eventually, I'll get just enough applied force. Let me take a while here. To overcome the friction. There it goes. I just overcame the friction, the static friction, and now the block will move. So it's kind of fun to play around with this, and it gives you a feel for how the different frictional forces work. Okay, so we're going to stop sharing that, and we'll go back to sharing the slides. Let's see if I can find it. There we go. Okay, so I think, yes, we're going to do a poll question now. So I'll start the poll going while you have a look at this. So we got 4 choices. Okay, let's start that going. All right, so there's our poll. So what's our scenario here? We have a block of mass little m, and it rests on top of a block of mass big M. A string attached to block big M is pulled so that its tension makes an angle above the horizontal as shown. The blocks accelerate towards the right together. So little m and big M are accelerating together. Okay. The question is, what is the direction of the frictional force being exerted on the top block? Okay. And our choices are to the right, to the left, there is no frictional force, or none of the above. So I want you to think about that little block on top. Think about the forces that are acting on it, and think about the direction that little block is accelerating. So there's no, it's saying there's no frictional force between the blocks, is what it's saying. Right, or no frictional force acting on the top block. That's what the third choice would be. It doesn't say anything here about what's going on between big M and the surface. I would say you could assume that was frictionless, but we're not worried about that. Okay, you don't actually need to know the coefficient of friction. All you need to know is that the blocks accelerate together towards the right. So the top block doesn't slide away from the bottom block. So you guys have to decide whether it's static or kinetic. I think it would actually be the same either way. So, all right, I think we're gonna do like 10 more seconds here. So if you're not sure, go ahead and guess. So 5, 4, 3, 2, 1. All right, so let's have a look at everybody's answers. So what do we got? We have, so the majority, not quite the majority, but the largest group is going for B. And we have another fairly big group going for A, and then another fairly big group going for C. So why don't we have a look at this problem? Okay, so what do we know? We know that little m is accelerating to the right. So that means there must be a net force on little m. I'm going to get rid of the pole now so we can see all of this. So we know that little m is accelerating to the right. So that means there must be a net force pointing to the right. Which force do you think is supplying that net force? Which force is causing little m to accelerate to the right? Friction, right? Right. Friction is causing little m to accelerate to the right. Okay? So that means, and then what kind of friction? Well, if little m is not moving relative to big M, and it isn't because they're moving together, then that is in fact your static friction. Okay, so we have a net force on little m, which is static friction. It's stopping little m from sliding away from big M, and it points to the right. Okay, so if little m is not moving relative to big M, it's static friction. Okay, if you pull hard enough, then the static friction won't be able to hold on, and little m will slide away. Basically, big M will slide out from underneath little m. Okay, this is a little tricky, this one, because you have to sort of go back to your Newton's second law and say, okay, I know F equals ma. I know which way little m is accelerating. It's to the right. Okay, and there's only one force pointing to the right on little a. Okay, the tension is not little m. The tension is not acting on little m. The tension is acting on big M. Okay, so it's not the tension. It's the force of big M on little m, which is a static frictional force to the right. Yes, it's to the right, so it's the same way as the acceleration. I don't know what you mean by momentum playing a part on little m. So. But anyway, I think we're going to move on from this one, and we're going to do an example problem. And this one is related to one of the problems in the pre-lecture videos. Okay, so it says a textbook is placed on a binder at an angle as shown. The coefficient of static friction between the book and the binder surfaces is mu s equals 0.5, and the coefficient of kinetic friction is mu k equals 0.35. And so the first question we're going to try and answer is, will the book slide? So if you put a book like this, so we're going to test, we're going to basically analyze it, okay, and see if it slides. And then if it does slide, we're going to figure out what its acceleration is. So let's start with, so this is straight out of the pre-lecture. So we know the force is acting on our book. Right, we have our normal force perpendicular to the surface of the binder acting on the book. We have now what we're going to do to figure out whether the book is sliding or not is we're going to look at whether the static friction is enough to stop it from sliding. Okay, so we're going to draw in a static frictional force resisting the motion. We know without friction it would just slide right on down the slope. And why? Because weight points vertically downwards, and that has a component down the slope. All right, so as usual, we're going to start with a free body diagram. So here's our XY axis, and typically with problems like this, with slopes, with what they call inclined planes, you want to have your positive X direction be down the slope or up the slope, whichever way you think the object is likely to accelerate. I think this object, if it does move, will accelerate down the slope, so I'm going to make my X down the slope. Okay, and then the normal force is in the positive y direction, and then we'll have my static friction in the negative x direction. So it looks like this. Here's my normal force pointing in the positive y. Here's my weight, which points between positive x and the negative y. And there's my static frictional force pointing in the negative x direction. Okay, so like I said, what we're trying to figure out, if it slides, basically what would cause it to slide is if the force down the slope is greater than the maximum static friction. So that's what we're going to try to figure out. Is the force down the slope greater than the maximum static friction? Then it will slide. Okay, so as we typically do with these two-dimensional problems, we start by writing down Newton's second law in 2 dimensions. So the sum of the forces in the x direction is the mass times the x acceleration. Sum of the forces in the y direction is the mass times the y acceleration. Okay. And then we know that that angle between the weight vector, our force due to gravity, and the negative y-axis is theta, where theta in this case is 30 degrees. Theta is our slope, right, of our inclined plane, that angle from the horizontal. All right, so I'm going to start actually with the y situation. So I'm going to look at the sum of the forces in the y direction, and I know that the y component of the weight is our mg cos theta here. Okay, so I'm going to look at the sum of the forces in the y direction. So the normal force points in the positive y direction. So we have positive the magnitude of the normal force and then minus the magnitude of the basically minus mg cos theta is the component of gravity in the y direction, and it's in the negative y direction, and that's why it has a minus sign. And we know those two have to add up to 0, okay, because there's no acceleration in the y direction. And so we get our normal force is mg cos theta. So that's going to happen pretty much unless there's some other force perpendicular to the surface. That's what your normal force will be for your inclined plane problems like this. And then that's what we saw in the pre-lecture. Okay. So now let's look at the x direction. So what do we have for the x direction? So we have the sum of the forces in the x direction is the component of gravity in the x direction, which is mg sine theta, okay, minus our static frictional force. Okay, and again, we know we've got our normal force, mg cos theta. Okay, so, and if we look at that, we can see that it'll slide if the net force in the x direction is positive. Okay, so it'll slide if mg sine theta is bigger than the maximum static friction. So what we're going to do is compare those two. Okay, we're going to look at mg sine theta, we're going to look at the max static friction, the magnitude of that, and compare them to each other. All right, so what's the max static friction? It's mu(s) times the normal force. So this is why we had to figure out the normal force. Okay, so it's mu(s) times your mg cos theta. Let's plug in some numbers. So this is mu(s), mg cosine 30. So it's 0.5 for our mu(s), mg times the cosine of 30 degrees, which is about 0.866. And you get about 0.433 times the weight of the book. Okay, so that's the maximum static friction. Now we're going to look at mg sine 30 degrees, okay, which is the component of the gravitational force or the component of the weight down the slope. And we know that's just equal, so sine of 30 is 0.5, so that's 0.5 times mg. And then we look at these two quantities, and we can see mg sine 30, which is 0.5 times mg, is greater than the maximum static frictional force, which is 0.433 times mg. And since mg sine 30 is bigger than Fs max, we know that our book will slide. Okay, so that's how you would figure that out. All right, you figure out how big is your maximum static friction, you compare it to how big is the force down the plane, and if it's big enough, then your object will slide. So are there any questions on that? Okay, so the second part of the question, I'm not actually going to do, because the second part of the question, oh, how do we know it's got to be bigger than mg sine theta? Because mg sine, oh no, okay. We know that the force of gravity down the slope has to be bigger than Fs max. Okay, so we know that mg sine theta has to be bigger than mu s mg cos theta. Okay, so like I was just saying, we're not going to go over the second part, which is how to figure out the acceleration, because that's the one they already did in the pre-lecture. It's exactly the same scenario, because now that you know it will slide, you switch to using your coefficient of kinetic friction, and you do the same thing. Look at the sum of the forces in the x direction, set it equal to mass times x acceleration. So I won't go over that because you have seen that already. What I am going to do is do another poll question on this topic, because this is an interesting one to look at, and this one is somewhat related to what you're going to do in tutorial this week. So we've got 5 choices here for this one. Okay, so we'll start this poll. And now we'll talk about this one. Okay, so we have a box and it's sitting on a flat board. Okay, and what you're going to do is you're going to lift one end of the board, making an angle with the floor. As you increase the angle, the box will eventually begin to slide. Okay, if you've never tried this, go ahead and try it. Just take like a notebook and put an object on it, and as you pick up one end, it'll slide down. And the question is, why? Okay, is it because the component of the force due to gravity parallel to the plane, okay, so along the slope, increases? Is it because the coefficient of static friction decreases? Is it because the normal force exerted by the board on the box decreases? Is it both A and C? Or is it all 3, A, B, and C? So you're basically looking at a scenario where you start flat, right? And then that angle theta increases. And eventually, if it gets steep enough, that box will slide. And I should say that picture there should include a frictional force, and it doesn't have it. So imagine there's a frictional force in that picture too. I just realized it should have a frictional force in it. All right, I think we're going to do 10 more seconds on this one. So if you're not sure, go ahead and guess. All right, 5, 4, 3, 2, 1. All right, let's see what everybody thought. Okay, so what do we have? We have the largest group, think it's D, both A and C. And the next largest group think it's at least A. Okay, so let's have a look at how this one works. So we're going to end that poll. All right, so what do we know? So if we look at the component of the force due to gravity parallel to the plane, which is mg sine theta, and we say, does that increase if theta increases? And the answer is that yes, mg sine theta increases as theta increases. So yes, A is correct. Okay. And then we look at the normal force exerted by the board on the box, and that's mg cos theta. And we say, what happens to cosine theta when theta increases? So what happens to cos theta when theta gets bigger? Can you tell me? When you go from 0 to 90 with the cosine function, what happens? Does it increase or decrease? It decreases. Good. So cosine decreases. Okay, so that's true too. So both A and C are true. Okay, both that the force due to gravity down the plane increases, the normal force decreases. Okay, the coefficient of static friction does not change. That's a fixed quantity that can't change. So therefore, our answer is both A and C. So well done. Most of you got that one right, or a large group of you guys got that one right. Because basically what's happening is as the angle increases, the component of the weight parallel to the plane increases and the normal force decreases. And because the normal force decreases, the max static frictional force gets smaller. Okay. And so that one gets smaller and the pulling force down the plane gets bigger. And so that's why it ultimately will slide. So you have two different things going on. Both the force down the plane is increasing and the max static friction is decreasing. Okay. And so one's getting bigger, one's getting smaller, and you just need that mg sine theta to be bigger than that max static friction, and it will slide. Okay, so yeah, B didn't say coefficient of static friction. Okay, if it just said static friction, then B would be right. But it said the coefficient of static friction. And that's a fixed number. All right, so now we're going to move on, and for the last part, we're going to look at centripetal force. So what is centripetal force? So centripetal force is the name we give the net force pointing towards the center of the circle that causes the centripetal acceleration of an object. It causes that force in towards, that acceleration, in towards the center of the circle when something is moving in uniform circular motion. Okay? And the main thing to realize with looking at uniform circular motion and forces, okay, first thing is we know how big centripetal acceleration is. We know its magnitude. Okay, so our centripetal force, Fc, is equal to the mass of the object times the centripetal acceleration. So they both point in the same direction. Okay, and we know the centripetal acceleration, its magnitude is v squared over r, the speed of the object divided by the r, the radius of the circle, right? So then that means the magnitude of the force is just m v squared over r. And when you're solving problems, okay, the main thing to realize is what you have to do for a given problem is to draw a free body diagram and analyze the forces acting on the object that's moving in the circle and determine the magnitude of the net force pointing towards the center of the circle and set that equal to the centripetal force. So set that equal to mv squared over r. Okay, so you're looking, the centripetal force is not a separate force, okay, that suddenly appears out of nowhere, okay? It's the sum of all of the forces pointing radially inwards. Okay, it's the net force pointing towards the center of the circle. So the net force pointing towards the center of the circle is equal to mv squared over r for an object moving in a circular path. So I thought we would try another poll on this. We're back to our ladybug revolution PHET, and we've got 4 choices here. And the ladybug is joined by a beetle on a turntable, a record turntable. And the question is, okay, so a ladybug and a beetle sit on a turntable spinning at a constant rate. So it's going around at, say, 33 1/3 revs per minute, RPM. And the question is, which force supplies the centripetal force that keeps them moving along a circular path? Okay, is it kinetic friction between their feet and the surface of the turntable? Let's assume they're standing on their feet. Is it static friction between their feet and the turntable, the surface of the turntable? Is it the normal force of the turntable on their feet? Or is it the force due to gravity, let's say on the ladybug or the beetle? I forgot to say what it was acting on. It does sound like a political movement. I think that's one of the reasons I like this PHET is because of the name. A friend of mine, actually, you can see this is a screenshot from a GIF. A friend of mine made a GIF that where they just go around and around and around. But I had trouble inserting it in my PowerPoint, so. Yeah, I think ladybugs would definitely be fighting for environmental rights for sure, and against global warming. So. All right, why don't we, let's do 10 more seconds on this one, because we have at least one more to go. I want to try to get at least both of the poll questions in. Okay, 5, 4, 3, 2, 1. Let's see who's still with us. Okay, so for everybody who's still with us, the largest group, the vast majority, are going for B, static friction, and another group, next biggest group, are going for A, kinetic friction. So we're sort of in a consensus that it's friction. So what does this look like? Well, so here's our centripetal force. Okay, there must be a net force pointing towards the center of the circle. We're looking at the ladybug now. If the ladybug is going to continue in her circular path. And so you can just kind of go through the forces and say, what could possibly be supplying that force? We know it's not the normal force or gravity. Those both point perpendicular to the surface, not along the surface. So that would be like in or out of the page. So it can't be one of those. And we know it's not kinetic friction. This is kind of similar to the block, the little block and the big block. We know it's not kinetic friction, okay, because the ladybug is not sliding relative to the surface. the surface and her are moving together. Okay, and since she's not sliding relative to the surface, it can't be kinetic friction, and so therefore it has to be static friction that's keeping her, and the same thing for the beetle. Okay, in fact, the beetle might need even more, right? Depending on the beetle's mass. He might need even more static friction, right? Because he's going to have a bigger centripetal acceleration because he's further out on his term table. So my next question for you is, what would happen if there was no friction? Or if there is no friction? What do you think would happen to our ladybug and our beetle? Yes, they would go, yeah, beetles, yeah, they would go flying off. Okay, they would essentially go flying off in a direction opposite to the direction that the centripetal force is currently pointing. Okay, and that's actually what happens inside the centrifuge. Some of you guys may have used the centrifuge, right, in lab, right? Basically, what's happening there is you've got things in a test tube that have no friction on them, and so when you spin, they essentially go flying out because there's no centripetal force to keep them along that circular path. Okay, so that's essentially, and that's why sometimes people say centrifugal force, because it looks like there's a force on you, but really in reality it's a lack of a force that supplies a centripetal force to keep you going in a circle. All right, we have another circular situation, and this one is related to one of the other tutorial questions, so I thought we would do this. This is a vertical circle. So let me start this one. This is a Ferris wheel. Yeah, the harder they splat on the wall, that's very true. Okay, here we go. We got 4 choices this time. Okay. So this is a Ferris wheel. I don't know how many of you guys have been on Ferris wheels. I quite like Ferris wheels. Okay, let's start that one going. So this is a Ferris wheel, and you have to imagine, okay, that you're sitting upright the whole time. So this is not one of these Ferris wheels where you go upside down at the top. So you have a rider on a Ferris wheel, and they're moving in a vertical circle at a constant speed. And we're looking at the normal force the seat exerts on the rider. Okay, so basically, so that upwards force of the seat on the rider. And the question is, we're comparing, saying the normal force that the seat exerts on the rider at the top of the wheel, okay, assuming the rider is upright, is that normal force greater than the normal force at the bottom of the wheel? Is it less than the normal force at the bottom of the wheel? Is it equal to the normal force at the bottom of the wheel? Or you can't figure it out? There's not enough information given. So they're moving in a circle, a vertical circle. So remember, that means there must be a centripetal acceleration pointing towards the center of the circle. So when you're at the top, the centripetal acceleration is down. And when you're at the bottom, the centripetal acceleration is up. And the acceleration due to gravity doesn't change. But there is gravity here. Yes, the person still has a weight, and that weight is going to contribute here. And the weight is always downwards. So when you're at the top, right, it's in the same direction as the centripetal acceleration. And when you're at the bottom, the weight is opposite to the centripetal acceleration. And it doesn't change gravity, but it does change how you perceive gravity. Because it turns out you perceive gravity via the normal force you feel. And the more normal force you feel, the heavier you feel. Okay, the acceleration might be small. Yeah, I think it's likely small. because they don't want you to pull too many G's, because that's not good. People passing out on Ferris wheels is not good. We're going to do an example in a minute if we have time, and you'll see that what the numbers look like typically. All right, I think we're going to try and finish this one up so we have time to have a quick look at the problem. So let's do 5 more seconds. So go ahead and guess if you're not sure, okay, how those two normal forces compare. So is the normal force at the top greater than, equal to, or less than the normal force at the bottom? Okay, so 5, 4, 3, 2, 1. And it looks like we almost have a tie. We have a three-way tie, okay, between greater, less than, or equal to the normal force at the bottom of the wheel. All right, so let's have a look at this one. So you can see some of these concepts are not always super straightforward right away until you play around with them, which is why we're doing them in class. So what we do now is start with looking at the top. So we know when you're at the top, the centripetal acceleration would point downwards. All right, and then you think about someone sitting in a seat. Okay, what are the forces acting on them in the vertical direction? There's a normal force up, and there's a weight down. Okay, and when you're at the top, the weight has to be bigger than the normal force so that your net force is downwards, so that your acceleration can be downwards. Okay, but when you're at the bottom, now your centripetal acceleration is upwards. So when you look at your vertical forces, now the normal force has to be bigger, and the weight, right, which is smaller relatively. Okay, now the weights are the same, okay, in each case, but relative sizes. I was trying to do relative sizes here. I should have drawn those weight vectors the same size. Sorry about that. Okay, but the idea is that the normal force is bigger than the weight at the bottom. Okay, I'll fix that before I post it. But the normal force is bigger at the bottom than the weight. So if the normal force is bigger than the weight at the bottom, but smaller than the weight at the top, the normal force is the one that varies. Okay, so then the normal force is smaller at the top. Okay, so the normal force at the top is less than the normal force at the bottom. If you've ever been on a Ferris wheel or the top of a roller coaster, okay, and you feel that slightly weightless or lighter feeling when you go over the top, that's what's going on, okay? Because when you're at the top of a curve, okay, then your normal force is reduced relative to your weight. Okay, and that's why you feel a little bit lighter. Sometimes we refer to this as your apparent weight. Your apparent weight is reduced when you're at the top of the arc. Okay, all right. The normal force can vary. The normal force doesn't have to always be equal to the weight. It depends, okay? Basically, the normal force plus the weight have to add up to the acceleration, okay, in that y direction. And so when you're at the top, it's less. And when you're at the bottom, it's actually more than the weight, because it's the normal force at the bottom that's giving you the centripetal force upwards. Okay? So at the bottom, when you come around the bottom on the Ferris wheel, you sometimes feel heavier. Okay? So that's what we're comparing, is the normal forces here. Okay? So the normal force at the top is much smaller, and the normal force at the bottom is larger than the weight. Okay? And we don't really have time to do the example, so I had an example problem set up. So I think we'll start with the example problem next time, so we can see, yeah, they would be this, you're right, the normal forces would be the same at the sides. Yes, that's absolutely right, because the centripetal force at the sides would be pointing either left or right. Okay, and it wouldn't be the normal force of the bottom of the seat on you that was causing the centripetal force there. Okay, so I think we'll stop there. And like I said, I'll start next time with that example problem. Okay, I think we're going to do some more force problems next time And then on Friday, we will get into chapter 6. So let's stop recording.